I wanted to do was start with you're solving your current assignment, and so I just wanted to this is a good point in the course to share this comment that if you're finding the course getting a little hard at this point, it's some of the founding people of semiconductor physics. This is a comment from them, from a very popular old textbook that semiconductor physics and physics of semiconductors and nanostructures involves clearly a lot of quantum mechanics, but also statistics. It involves quite a bit of crystallography, thermodynamics, and chemistry. And so according to them, at least, it's incredible what miserable quantities of thought and mathematics are needed to explain the simplest things. But I think it's just to kind of make sure that if you are feeling at this stage, if you're feeling it's okay, no problem. If you're feeling that it is the concepts are not quite solid and are not very clear yet, I just wanted to ensure that this is how everybody starts learning this subject, and it is because of the nature of the subjects. But essentially, the only way to learn is not just is essentially. We can learn quite a bit in lectures, but really you need to solve the problems, and if you just work through them. Do not kind of give up on them. Just work through it. It'll be okay. And we have what we have done is essentially in many of the semiconductor physics courses you can get by not discussing what's under the hood. You can get by with a little bit of hand waving. We're not doing that here. We're kind of going all in some sense, so and I think it on the whole, if you essentially work through it, we have developed a very powerful range of tools. So if you get some practice with them, and the transition from no idea how to attack a problem to if you get the concept for one, it's very general. For example, right now we're doing currents, right? We talked a little bit about doping, and the way we treated it is really very general. It can be applied to currents in superconductors, currents in amorphous materials, wherever. So we are developing it for this material right now. So okay, just to kind of make sure that, and then this is it's that stage of the course. If you're feeling that way, I just wanted to ensure that the rest of the course really is a lot of applications of what we have developed till now, so you'll see it becoming clearer and clearer. Okay, so what I wanted to do was today in this class is kind of also do a rough summary of the things we have developed since last midterm. So the basic idea really that we have developed is when an electron is going through any sort of a crystal, be it a semiconductor or a metal, it has the allowed energies are dependent upon the k or a wave vector, and so just like a hydrogen atom may have different energy states, it's just like that, except if it starts moving in a certain direction, the energies change, and these are the eigenvalues, and that's the band structure of semiconductors. And we talked about silicon has a band structure like this. We talked a little bit about what are these points in k space, gamma point, the 0, point, and different directions in the k space. And based on that, we talked about band gaps can be indirect, like maximum of the valence band and minimum of conduction band can be in different points in k space, or they can be direct, like gallium arsenide, where the minimum here and the maximum here are the same point. Now, what I wanted to do now is talk a little bit about going beyond it, and your last problem of the current assignment is an example of what you call as a heterostructure. It's two different crystals, against each other, right? Two different crystals can be two semiconductors. They can be two semiconductors with different doping. That's typically not called as a heterostructure, it's called a homostructure, but I'll discuss this. Or they can be one semiconductor or and the other is a metal. This is also heterostructure, right? So before we go to heterostructures, let's just talk about what are the range of semiconductors we can now explain with the understanding we have in this course. So we have already, you have done some modeling of silicon band structure. So that would be a group 4 semiconductor, silicon, and by changing all your tight binding parameters, you can get the band structure of germanium or diamond or any of those, right? So you can kind of, you did a band structure for gallium arsenide. And again, so this is a group 3-5 semiconductor. So the group 3 of boron, aluminum, gallium, and group 5. Gallium arsenide is here, as you can see, or gallium phosphide or gallium antimonide. These are group 3-5 semiconductors. So one from group 3, one from group 5. Remember, they are tetrahedrally bonded. Each atom is bonded to 4 other, right? And so each bond is formed because of 2 electrons. Therefore, your minimum basis is 2 atoms. Just like silicon crystal has 2 silicon atoms as the basis, gallium arsenide has gallium and arsenic. So the total number of valence electrons, when you sum them, should be 8 because there are 4 bonds and there are 2 electrons each in each bond in a unit of the crystal. So therefore, you have 3 plus 5 is 8. You can do 2 plus 6 is also 8. So you can get a 2,6 semiconductor. The green, not very clear here, but so zinc and oxygen, zinc oxide is a 2,6 semiconductor. Zinc and sulfur, zinc sulfide, zinc selenide, these are all 2,6 semiconductors. Right? So that's group 2,6 or zinc, so these are mercury telluride, that's an interesting semiconductor, mercury with tellurium. So general trend is as you go up in the periodic table, as you go to lighter and lighter atoms, your band gap increases. The band gap goes up, and I'll emphasize it later as well. So band gap goes up, and as you go down in periodic table, the band gap shrinks. By the time you're down here, you have metals. These are metals, zero negative gap. Basically, there's no fundamental gap. And within the same family also, if you look at, for example, aluminum nitride, that semiconductor or almost an insulator has a gap of 6 electron volts. Gallium nitride, 3.4 electron volts. Indium nitride, 0.6 electron volts. This was a major unresolved band gap. A lot of it was done in Phillips Hall here. They discovered the band gap here, and some groups in Russia simultaneously discovered around 2002 that the gap was much smaller than what people had thought before. So indium nitride. And so that's how you can go from 6 eV to 0.6 eV, 10, factor of 10 shrinking by just stepping down in the periodic table here. Okay, so similarly, diamond, has a band gap of close to 6 electron volts. Silicon is 1.1, germanium is 0.6 or so. By the time you reach 10, you are metallic. It's kind of a band start overlapping. So, yeah.
Are there certain applications that each group is used for?
Absolutely, yes, absolutely, yeah. So, it's a great question. And so group 4, as you know, silicon is predominantly used for electronics, for digital electronics. So, and one of the main reasons, many reasons, but silicon is abundant. So if you look at vast shores of it's all silicon dioxide, you can really mine from just sand, right? But also so it's an indirect bandgap semiconductor. So though it's extremely good for digital electronics, it cannot emit light. So that's because of this thing. So because of the indirect band gap, therefore the direct band gap semiconductors occur in group 3-5 semiconductors. That's where the direct band gap semiconductors occur. Gallium arsenide, gallium nitride, these are direct band gaps, so they can emit and absorb light much more efficiently. So for optoelectronics or photonics, where you want to make lasers, LEDs, and all that, so there silicon is not playing any role. Gallium arsenide and gallium nitride are, right? So all the visible or infrared lasers, 1.55 micron laser, the ones that power all of telecom today, a lot of telecom today with optical fibers, those are built with gallium arsenide based gallium arsenide and indium gallium arsenide heterostructures. So and similarly, group zinc oxide. It's used for zinc oxide has a gap of 3.3 electron volts. One of the interesting things about zinc oxide is it can occur as nanoparticles. You can easily synthesize them, and then we put it in an ointment, and that's your sunscreen, right? So it absorbs UV light. because its gap is 3.4 electron volts and UV light is slightly more than that. So it's a one. Probably that's the widest or highest volume usage of this material. But there's also indium, gallium, zinc oxide. These are TFTs for big screen TVs. These are thin film transistors, IGZO, and that sort of thing. So anyway, so there are kind of lots of uses. Even the ones which are very, very small band gap, mercury telluride, HGTE. This is a very, very small band gap semiconductor. The gap is in tens of milli-electron volts. It's a very, very small gap. And what it's used for today is for night vision imaging. So if your aircraft is flying above or you have goggles and you want to look at what's happening in the night, you can image using infrared radiation, right? Heat. Heat is also photons. These are infrared, but these are very small energy. These are about tens of milli-electron volts. So if you choose a semiconductor with a band gap where the gap is only tens of milli-electron volts, and it absorbs a heat light in a light, essentially, which is infrared light, then it can, even with because the photon energy is very small, it can excite a lot of carriers from one band to another. And instead of heat, you can image using that. And so night vision imaging uses mercury telluride or mercury cadmium telluride, MCT. That's the name that's used for night vision imaging. Quite a few applications, especially fighter aircrafts. They use that. You have to kind of cool it down a little bit. Otherwise, if not, just the room temperature interband thermal ionization is going to swamp out. So you have to cool it down. Similarly, it's used a lot for space exploration and that sort of thing. So all of them have different uses. So more recently, a lot of interest in two-dimensional semiconductors, which combine, for example, moly with two sulfur atoms, MOS2, moly disulfide. That's atomic. Basically a three sulfur, moly, and sulfur, and that's all. It's a two-dimensional sort of semiconductor. Band gap of roughly 1.8 electron volts or so, or tungsten sulfide, tungsten selenide. You can also make group 4,4 depending upon the crystal, as long as your chemical, electron counting is okay, and you get gallium selenide. That's another semiconductor, but here you can see the groups are a little off, 3 and 6. That means in a unit cell you can't have just one gallium and one selenium. So you have to have a little more, and that sort of thing. So some of the earliest semiconductors that were, before even the name semiconductor was coined, were based on copper sulfide, copper and sulfur, CuS2, or iodides and that sort of thing. So these are not used much more now, but also if you look at old buildings, with copper domes, you see a little green color, right, when they start rusting, and that's copper oxide, CuO, which is also a semiconductor with a band gap around green, which is 2.4 eV or so. So that's why the color is green, and so on, right? So, but I'm going to focus a little bit more on the ones which are right around here, which are either for electronics or photonic sort of applications, and we're going to talk a little bit about that now. So there's a wide range of materials. And that's what really makes it so interesting and so powerful in terms of applications as well. Why? Because you can actually choose. So for example, here's a very nice chart which shows the band gap of a semiconductor like gallium arsenide or indium phosphide. These are group 3,5 elements. And as a function of the lattice constant, here's the lattice constant of the semiconductor, right? So gallium arsenide has a band gap of about 1.4 electron volts. And the lattice constant is about 5.65 angstroms, right? So that's the lattice constant. This is not the distance between two atoms, right? This is the lattice constant, which is that unit, the cell that we talked about, and so on. Right? So the distance between two atoms is close to this, slightly smaller than this. That's 2.5 angstroms. So yeah.
What are the lines? Because they.
Which lines are you talking about?
Any of them.
Yeah, I'm going to describe them now. So this is clear. So for one of the trends you observe right now is there's no reason to join them here, but actually there is. I'll describe now why are they joined and what's the understanding behind that. First trend is you see it's kind of going down like this, right? So as the lattice constant grows larger, the gap will become smaller, and this you can explain from your tight binding model straight away. essentially as the atoms are, so the bandwidth is changing with lattice constant, and as the bandwidths change, so do the gaps and all that. So as a result, the trend is downwards, and this is a general trend in the periodic table. If you're going down, the gap is decreasing. If you're going up, the gap is increasing. So yeah. Right. So let's look at the simpler lines here. There are vertical lines, the dashed lines. And these dashed lines are very important because what they're showing is if I have gallium arsenide and if I draw a vertical line and I find something here which is aluminum arsenide, there's another semiconductor with a larger gap, okay? Then the lattice constants are very, very close to each other. The vertical line shows something called lattice matching. You can actually deposit an aluminum arsenide layer on top of gallium arsenide without creating defects. There will be very little strain. So lattice matching is when you go this way. And let's say I choose indium phosphide. Okay. Now on indium phosphide there is no other binary semiconductor that I can grow with no lattice mismatch. So if the lattice constant, there's no other thing. But you can see there are all these lines that are crossing it, right? And these lines are when, for example, I take gallium arsenide, and here's indium arsenide, and I can actually grow by epitaxy, like molecular beam epitaxy or chemical vapor deposition. I can grow an alloy of these two materials. So for example, let's say 50% of indium, 50% of gallium, and arsenic. So 50% of the metal sites, gallium sites, or group 3 sites are occupied by indium, and the other 50 by gallium. Right? And so you have an alloy of indium, gallium arsenide. It's in gas. That's the name it's used. And you'll fall somewhere around here. And this is a crystal, right? And you can now lattice match to that indium phosphide now. So you have this incredible. So essentially, what these lines are showing that by the control of the materials that you grow, you can go from here all the way till here. All these points are completely accessible, and not only accessible, they are heavily used in semiconductor devices. So these are so essentially in the periodic table now you can basically the whole space between them is also occupied. So by these mixed or the alloy systems. Yeah.
Is that commensurate or is that fully lax?
This is completely crystalline and completely commensurate. And you can grow. For example, you could grow half a micron of this on top of this, and there will be it will be a perfect crystal. Perfect crystal in the same, on the average it will be indium gallium arsenide. There will be no dislocations, there will be no strain. You can grow very, very thick that way. So and this is one of the real very powerful tools in semiconductor heterostructure physics, that you can actually mix two bandgap semiconductors, and you can now start designing a lot of things that I'll talk about now. Okay? So you can go indium phosphide if you choose aluminum. So let's go along this line: aluminum, indium arsenide, Al indium arsenide. You can get a larger band gap than indium phosphide, and by indium gallium arsenide you can get a smaller band gap, and you can kind of grow heterostructures of these three. You can some larger gap, some smaller gap. You can kind of start going and designing the thicknesses, and then start designing the whole structure, and go and grow them. And actually, if they are lattice matched, you can grow them without any defect generation. So that's kind of very nice. As you may imagine, if you go down to very small, okay, so that's the vertical line, and these lines are all. If you see solid line here, that means that if you have formed that alloy, let's say you've formed about 50%, actually it's close to probably more like 40% indium and 60% gallium to lattice match with this. So that these solid lines are these are direct bandgap semiconductors. So for those alloys, also your band structure looks like this: the minimum of conduction band and the maximum valence band at the same point in K space. Does it make sense? So those are all direct bandgap semiconductors. But if there's a little window here where you go indirect, where that conduction band minima goes slightly off gamma point, and then what happens is then this goes slightly off in that little window that we talked about here, the dashed line here, in which case that thing will not emit light efficiently. So it becomes so that this is, people have figured this out over the last 20-30 years with great detail, and because of also extremely useful for applications. So similarly here, you start adding aluminum to gallium antimonide, until here it remains direct, and then it goes indirect. Aluminum arsenide is indirect bandgap, and all the way till here it's indirect. Gallium phosphide is indirect bandgap. This is right around slightly with some, or this is around red color. So the old red LEDs that you see in all kinds of displays were made with this sort of material here, but with nitrogen doping and all that. There's a question.
Does that mean that there's a minimum value of the lattice constant you can have if you want to create an optical, or to have a direct bandgap?
Minimum value of lattice
It looks
constant.
like below like 5.5.
Oh, I see.
You don't
So.
have direct.
I see. So that's yeah. So that's in this family of semiconductors. So you can go to So for example, I can go to gallium nitride system where the lattice constant is much smaller and the gaps incidentally are much larger because of that. So gallium nitride system, lattice constant. So it's also a hexagonal crystal. There's a slight difference, but in general, it's a much smaller lattice constant, and the gaps are about. I think I don't. So it's about 3.4 electron volts. So if you use gallium nitride, you're in UV, but if you start adding indium to it, you start getting into blue. These are all direct, and then green, and then yellow and red, and so on. So, and here's what I was mentioning, that you can actually grow even though you're lattice mismatched. So I mentioned earlier that if you are lattice matched, if you're along these vertical lines, you can grow pretty thick layers without relaxing. And then how thick can you grow? I'm not going to cover that in detail, but you have an order of magnitude, which is if you take the difference. So if you grow a different lattice constant than the substrate, if it has a larger lattice constant than this layer, then beyond a certain thickness, the strain energy will overcome the. So essentially, there'll be the strain energy will try to relax, and as a result, there's a critical thickness, and that critical thickness, just rule of thumb, is roughly equal to the substrate lattice constant divided by twice the strain. And strain is just the difference in lattice constant divided by the equilibrium lattice constant. So that's very simple sort of thing. So for example, if your lattice constant is 5 angstrom and your strain is 1%, right? So you have 5 angstroms divided by 2 times 0.01, right? So what you have is 500 over 2, so 250. You can grow about 25 nanometers, order of magnitude, of something that is 1% lattice mismatched with a substrate of 5 angstrom lattice constant. So it's just order of magnitude. You generally can be a little more because this is, there's a Matthew Blakesley sort of relation. So here's an experiment from a lab, for example. I don't know whether you can see. We are trying to grow aluminum nitride on GaN. There's a lattice mismatch. And once we exceed 8 nanometers, you can see cracks and dislocations form and all that sort of thing. So yeah. But there is a nice window within which you can grow these layers. And for example, if you grow indium gallium nitride on gallium nitride, so indium gallium nitride, let's say you are here about 20% or maybe about 10 or 15% of indium to gallium, you add that. And here's a layer that's grown, which is very thin. I know it's not very easily seen, but it's very thin, a few nanometers of indium gallium nitride. So that would be a quantum well inside gallium nitride, which is a larger band gap here. So if you are able to put electrons and holes into this layer, it is going to emit light of blue color. So that's what so you kind of design this out, and then and it emits light of blue color, and that's what is today used for all the LEDs, and the white light source is based on a blue LED which pumps a phosphor, and the blue is, as you know, the shortest wavelength or near UV, but it's the shortest wavelength, and so that the white. Most of the white light sources, including, I just wanted to pull this out. So this is a gallium nitride LED. It has those quantum wells inside, the white LED in your cell phone. And all the LEDs that are around here are also gallium nitride LEDs that do the, lighting, the brighten up the thing. So they have like about 3 or 4 quantum wells inside. So blue, you can by changing indium composition, you increase the indium a little bit. You can go green or yellow or red and all that. So you can kind of do this sort of thing. You take a LED, put some mirrors around it in a semiconductor, and you can make a laser with it. So the blue laser diode is built that way. So it's based on semiconductors, and it has this active region inside. Okay, so just to so in addition to the band gaps, another very important quantity is the band offset, meaning, as you know, the band gap is one thing. So here's silicon; it has a band gap of 1.1 eV, but the conduction band is here and the valence band is here. And this plot is kind of an important plot because it is plotted with respect to vacuum level. Here's the vacuum level, the energy of an electron if it was not in the semiconductor but in vacuum, a free electron would be here. Not moving, zero kinetic energy.
What's the symbol for that again?
Of what?
Vacuum level. Energy of vacuum.
So your question is, what is the symbol?
Yeah, because if we wanted to do, write out the difference between two energy levels.
Got it. Yeah. I'm going to actually write down this on the board now. So yeah. So the vacuum level is when the electron is completely escaped the clause or the binding forces of the crystal. It's completely free now, and it's not tied to the crystal. Whereas, so essentially what it means is if I have an electron in the conduction band at the bottom of the conduction band of silicon, it has an energy that is about 3.8 eV below the vacuum. Right? That's what it means, below the vacuum energy. So that's its stability. So just by heating a piece of silicon crystal, I have no chance of kind of getting that electron to escape from silicon crystal. Does that make sense? I mean, heat is only like a few tens of milli-electron volts. Whereas if I shoot it with light of about 4 eV, I have a chance to kick it out. So that's Einstein's photoelectric effect, right? So where you can use light to kick it. Yeah, question.
What is the red dashes?
Yeah, so the red dashes, so this is a paper that I'm getting there. Okay, so that's the conduction band minima, and that's vacuum level. You can call it, label it as E vacuum or something like that, and I'll use that. And here's the valence band, and that means all the states below that energy are filled, and all the states above it are empty, conduction band, and so on. Now that's for silicon. Now if I have germanium, it also has a band gap, but it's so the one of the characteristic quantities about a semiconductor is the energy difference between vacuum level and the band edge, the conduction band edge. And that thing is called the electron affinity of a semiconductor. The electron affinity is just the name, but physically it's clear that it's a vacuum level to conduction band energy. The electron affinity is labeled by chi, and I'll write that down now. So similarly, germanium has a different electron affinity from vacuum till the conduction band. And so that means that the bands, if I try to grow germanium on top of silicon, the bands will line up like that. The conduction band of germanium will be slightly higher than the conduction band of silicon. Make sense? I mean, so that's how they'll line up. So the bands, the conduction band will line up in a certain way, and the valence band has to follow because the band gap is fixed, right? Band gap of the bulk material is fixed. And for of the bulk material, if you quantize it, you can change it now. But these are the band offsets, and band offsets can be of 3 types. So if I put 2 semiconductors together, the band gap of the narrower gap material can be completely inside the band gap of the wider band gap material. That's called type 1. These are heterostructures now, 2 different semiconductors joined to each other. That's called type 1, and you can see both delta EC is kind of going up here. So if I have an electron in the narrow bandgap material, it has to climb a barrier to go to the wider bandgap. If I have a hole here, it also has to kind of go over this barrier. This is a barrier for holes, if you want, or you want to think of electron going from here to there. That's a barrier for electrons, the same thing. So this is type 1. This is type 2 when one side is a barrier, but the other side is not a barrier. Does that make sense? It's type 2. You can see topologically there are only 3 cases that are possible in this situation, and the third is called broken when the gap is completely outside the gap of that. The bands line up in like that, right? And then there's like that, and then there's like that. Right? So there's 3 types of band offsets. And the nature of this gives you an incredible amount of freedom to design nanostructures and heterostructures for doing things. So for example, if you want to confine electrons and holes, you can take this layer, you can take material B and grow a very thin well of B inside A on this side and A on that side, right? Then you have a potential well for electrons, and you also have potential well for holes. You can confine both. Right? If you want to confine only electrons, but you want the holes to be kicked out of there, then you can choose this structure, in which case the electrons have a huge potential barrier. Holes always want to be on the top of the valence band, remember, so they want to bubble up to the top, right? So, but if you have holes here, it will not stay in this layer, it will go there. Right? So this is a asymmetric structure where you want to, confine only one type of carrier, but you don't want to confine the other. And this is extremely weird, but this has won people like 3 Nobel Prizes, that you can actually take 2 types of carriers, electrons and holes, and we'll talk about it a little more later. But if I have a field internally, electrons should go one way and holes, negative charges should go one way, positive charge should go the other way. But here you can force both of them to go in one direction, or you can force one of them to not respond at all to external electric field and the other to accelerate. So this is sort of a broken symmetry, which is a very powerful capability of semiconductor heterostructures, and we'll talk about that a little bit more later. But these are the 3 heterostructure possibilities, and what I want to now show is if I take instead of so semiconductors and semiconductor junctions, two semiconductors with different band gap, different doping, or a metal and a semiconductor. How do I look at this heterostructure and look at transport, look at electrostatics and band alignments and all that? I want to just talk about that now. Okay, so that's what we'll do for the rest of the class today. So let's just switch it on. Wait. All right. And now we have to play this one, right? Okay, so let's first start with the metal and semiconductor. Okay, metal and semiconductor heterostructure, and so we'll first look at a complete band structure detail, and then go to the band diagram. We start with band structure, then go to band diagram. Band structure is EK, and band diagram is energy minima versus space. So the band structure of a metal, and I'm going to just sketch it in this way, something like that. These are EK diagram for a versus K. Okay. And band structure for a semiconductor is similar, right? Not much really different as far as the band structure goes. I mean, obviously, there are some details that can be different. What makes the big difference between the band structure of a metal and a semiconductor? Yeah, exactly. It's the occupation, right? Where are the electrons, right? So band structure itself is they are different for the metal and the semiconductor. But on the whole, if both are, say, FCC crystals, then the nearly free electron model is pretty much similar, right? In which case, the band structure is not very different. But what's different now between the metal and the semiconductor, as far as the EK diagram goes, right? I'm going to just try to make a copy of that here. Something like that, right? Let's say the metal is filled all the way to, it's kind of almost half filled. So this band is almost completely filled, and you run out of electrons here in the metal. So that would be a metal, right? Maybe I should exaggerate a little bit, or so something like that. That's maybe a little better way to look at it. So I am filled all the way till here, and that's your metal band structure. And obviously all the states below it are filled and all that, right? But then you have a huge part here, which is empty states, right, in a band. Right? So this is high conductivity situation and all that. Right? Now the semiconductor. Okay, so that's your metal. And now if you ask me, where is the vacuum level here, as we were asking earlier, right? Where's the vacuum level? And the vacuum level, you can take the metal. If it's aluminum, you can do Einstein's photoelectric experiment and start shooting photons at it, increase the photon energy. At some point you will see it will start ejecting electrons, and you can measure where is the electron affinity, or the work function. So So the vacuum level, I'm just going to draw a line here. Let's say VAC, that's the vacuum level. And I've done experimentally, I've measured it. And I think with modern DFT first principles, you can calculate it reasonably accurately as well. So you can give me an estimate of what are the typical. So this is the work function, right? Q times phi sub m, that's the notation. The work function of a metal. Fermi energy, vacuum to Fermi energy. What's the order of magnitude for typical work functions? 5 eV, 10 eV. Yeah. So yeah. See, so there's a range around 5. So it would go from about like 3 to about 6 point some, maybe 7. 7 is pushing. So 6.5 eV or something like that. 3. So there are metals with about 3 electron volts, and then there are about 6 electron volts or so. That's the range of metals we have. Yeah. Now, this will have a rather complicated Fermi surface, though. The way I've sketched it. I think there may be, we saw a few copper, for example, has a very interesting Fermi surfaces and all that. But as far as semiconductor part of this goes, we will not have to bother too much, at least, about the Fermi EK diagram as much as the energy itself. And so this is the Fermi level of the metal, right? Let's label it as EF sub m. Okay. Now, let's come to the semiconductor. So where is the Fermi level of the semiconductor? Gap. So you see, it's an ill-defined question a little bit, right? So why? Because, yeah, exactly. The Fermi level of a metal, you can't change it, right? But a semiconductor is entirely up to you. You can change it over a range of magnitudes, right? You can go from very close to the valence band all the way to very close to the conduction band, maybe inside it, depending upon how much you dope and what type you dope. Right? So the work function of a semiconductor, let's say vacuum level, it's shared. I mean, vacuum level is the same for both before you put them together. So the vacuum level is here. So let's say I have doped it n-type, right? And now the minimum of conduction band energy to the vacuum level, on the other hand, does not depend upon how you dope it. And that's called the electron affinity. And typically it's labeled with this Greek letter chi. Chi sub s is the electron affinity of that semiconductor. But doping will place your Fermi level somewhere, and that's what you guys are doing. So let's say I've doped it n-type, and I place my Fermi level here. Again, you can see that is up to you. You can choose where you want to put it, right? So in which case, the work function of a semiconductor, the work function definition remains the same. It is from the vacuum level to the Fermi level of any material, right? Whether it's metal, whether it's semiconductor, it doesn't matter, right? So that would be called the work function of the semiconductor, phi sub s, right? And so, and if these materials are far apart and you have not formed a heterojunction between them, they will, they're stable. There's no need. I mean, the Fermi level is going to be here, and it's going to stay that way. Fermi level of the metal is here; it's going to just stay that way. There's nothing interesting other than that's the steady state situation. But now the interesting thing happens when you put them together, right? When you deposit a layer of aluminum on top of silicon n-type dope, for example, right? Then you form a Schottky barrier. So we now want to see why. What happens when you put the two things together, right? So, and everything that happens in a heterojunction is because of the drive of this combined system to have the same Fermi level. So the Fermi level is a measure of how many, is a count or a measure of how many electrons there are in this solid, in this crystal, right? So the electrons will always try to go from a region that has a higher Fermi level to a region that has a lower Fermi level. So that's period. I mean, they will always try to go from a region of high Fermi level to a low Fermi level, just like water tries to go from high level to low level and try to equilibrate. Same deal. So they'll try to go from high Fermi level to low Fermi level. So you might think, oh, semiconductor has no electrons. Not so. Semiconductor, in this case, has more electrons than this metal, right? In fact, it has electron energy is higher than the Fermi level here. So as a result, when you put these two together, the semiconductor is going to lose some electrons, right? And those electrons will end up in the metal. the metal will become negatively charged, the semiconductor will become positively charged. Right? Does that make sense? I mean, wherever the Fermi level is has a veto power on this, there's nothing that can stop this, So this charge will kind of go out. Now, how long it will take is a separate matter. So how it may take, 20 years, right, for some cases, or it may take 20 picoseconds, right? When it takes 20 years, that's why we build memory, semiconductor memory. So that's your semiconductor. That's the basis of semiconductor memory. It's kind of, you can hold it in that state for a very long time. And when you, but in general, I mean, we are okay. So if you're not doing memory, so it can happen very fast, right? We are looking at situations now where this equilibrium reaches very fast, right? So we're going to look at those first. So I'm going to put the two together, and so this is a so this is a EK diagram, and this is going to be under the hood now. I'm going to draw the band diagram now, right? Where the understanding is the minimum of conduction band and the maximum of the valence band is, and I'm going to draw it that we're going to call as EC, that we're the maximum as EV, and we're going to draw EC and EV versus space now, right? Not versus K anymore. Right? So I'm going to erase this now, or let me draw it on this side. So for the metal, there's only one level, and that's the Fermi level, right? So there's only one energy level, and so I plot that, E Fermi level of the metal, and I can, let's plot it here, Fermi level of the metal, and then there's a vacuum level somewhere here, and you will see that vacuum level will go away in the problem because it's a common thing between two. It will go away later, but it's conceptually it's important. And I'm going to just kind of shade these, saying that these are full of electrons now, right? Below the Fermi level. Semiconductor, the one we have chosen here, is lined up with vacuum such that so I'm going to draw the vacuum level as a constant initially, and you'll see rather surprisingly that the vacuum level is going to bend inside a junction. And okay, so here's for example my band diagram, EC and EV. Valence band is full, Fermi level somewhere here. I'm drawing a dashed line. Conduction band has some electrons. I'm not sketching it. It's very low compared to the valence band. So yeah. And then just to label everything again, here we are talking about space X and Q metal work function, Q times electron affinity of the semiconductor, and here to there is Q times the work function of the semiconductor, right? So that's how we have defined all these quantities now, right? And what I was trying to get to is because the Fermi level is higher here, Fermi level of the semiconductor is larger. Now this you can prove it why the Fermi level should be exactly equal by writing down thermodynamic relations and all, but this is the end result, right, of the thermodynamics, that the energy will be lowered by, and you will reach equilibrium, and after you reach equilibrium there will be one Fermi level throughout the whole system, right? There's only one Fermi level in all points in space at equilibrium till you apply a bias and all that sort of thing, apply an external bias. So here what we're saying is there are a few electrons in the conduction band, right? This is full. But you can see from your Fermi level alignment that this semiconductor must lose electrons to this structure on this side, right? And there's so when I try to physically join them, or in other words, I have a semiconductor surface, I clean it, and then I deposit metal in the clean room, right? Then and if this was N-type, then it must lose electrons, and I think that the only way to lose electrons from an N-type semiconductor is what? How will it lose electrons? Basically, if electrons go away, this region here, so the semiconductor itself is completely charge neutral, right? But if you lose electrons, it becomes positively charged now, right? Where are those positive charges coming from? Sorry? Yeah. Valence band is one possibility where you get holes, right? But even before that, you can get positive charge here, because where did those electrons come from in the first place, right? From dopants, right? Donors, right? You put donors in, that's how you put your Fermi level here. So you put a certain amount of donors, and we are saying that electron density is roughly equal to that, which is Nc to the power minus Ec minus Ef over Kt, right? And all that. So if I give you the donor density, that there are donor atoms sitting here, and the donor atoms will lose the electrons. They were hovering around here, but now when I put it in the junction, the electrons transfer into the metal. Okay? And as a result, the Fermi level, let me sketch what will happen here. So this is the intermediate situation before you have reached equilibrium. After you reach equilibrium, here's the band diagram now. Okay? And let me sketch it out first, then we discuss it a little bit more. Yeah. This becomes flat. So after you have reached equilibrium, there's only one Fermi level. You don't have to label with metal or semiconductor anymore. There's only one. Right? And so what has happened now is a certain thickness from the surface, which is x sub d, which is called the depletion thickness. Over that thickness, you have lost electrons from here to there. They're transferred from here to there. And what's left behind are positive donor atoms in the crystal. I mean, this is somewhere in the crystal, and they are not mobile. They can't move, but they are fixed in the crystal, right? And then you kind of go over to this side, and then there are the same free electrons kind of here, but very few here. In fact, the electron density is going down exponentially as you are going this way, right? Why? Because your conduction band is moving away from Fermi level as you go, right? So your electron density is spatially decreasing exponentially as you go from here to there. Make sense? So that. Now, the reason the bands bend that way and all that, so if I were to sketch the electron density, sorry, I'm going to just try to do a very rough sketch here. And it's so the net charge is in the system. The metal, deep inside the metal, no net charge, it's neutral. But electrons came from semiconductor into the metal, and in a metal at DC, all charge must reside only at the surface, not in the bulk. So all the electrons that came from the semiconductor into the metal kind of bunch up, and you form what you call as a 2D sheet on the surface of the metal, a two-dimensional sheet. And inside the semiconductor, far out on the right side, it's also charge neutral. But here, it's not charge neutral. It's positively charged because there are only donors, ionized donors. So you have a bulk of positive donors, positive charges, kind of spread out here. The value of the doping is Nd, so that's roughly the doping density in volume density sheet. Right? And therefore, and so essentially this is a fixed. If your doping is constant, it's a constant positive charge. So I'm plotting here charge density, rho of x, for example, right? Volume charge density. And this is depletion thickness. And the whole thing is always charge neutral. No matter how much charge transfer you do, if you look at the combined system, it's always charge neutral. Right? And to maintain charge neutrality, the total integrated area here must be equal to the sheet charge here. So as a result, the sheet charge in the metal that you will get, sheet charge in the metal is equal to the doping density times the depletion thickness. So order of magnitude, let's say doping density is 10 to the power 17 per centimeter cube. Depletion thickness depends actually on the barrier height and all, but it's of the order of 100 nanometers, of the order. And so when you take the two, when you multiply the two, you get 10 to the power 17. 100 nanometers is 10 to the power minus 5, so you get about 10 to the power 12 per centimeter square is the sheet density of charges. And this is a give or take the sheet density at pretty much every heterojunction you can ever encounter in metal semiconductor or semiconductor junction. Order of magnitude of sheet density is about 10 to the power 12, right? On a silicon MOSFET. So this is roughly the order of magnitude. Yeah. Sorry? Yeah. So these are order of magnitude. I mean, you can change it. You can make it a micron. That would be 1,000 nanometers. Or you can make it 10 nanometer to make a tunnel junction and all that. So this is up to you. You can change the doping and do this sort of this engineering. You can engineer it. Right? Now, looking at the band diagram, here, if I bring back my vacuum level, the vacuum level is here for the metal. So in the metal, the bands can't bend because there is no electric field. There's no inside a metal, so there's no voltage drop. Right? In a semiconductor, of course, there's voltage drop, right? So you can drop voltage, and to drop a voltage, you need charge, right? And so you have the charge. In a metal inside, you can't do that. So the vacuum level is here, and so once you enter the semiconductor, the vacuum level must, the electron affinity is not changing as you go in, so the vacuum level must do this inside the semiconductor. And as a result, this is a first order of magnitude. There are more complicated theories for this, but as a result, you can estimate that the barrier height for an electron to go from the metal into the semiconductor, this is the barrier now, because remember, this is a gap. These energies are not allowed because it's a periodic crystal and all that. We know why the gap, or where the gap comes from. So the electron, if it wants to go, an electron sitting right here in the metal, if it wants to go into the semiconductor, it must surmount this barrier. This is a classical barrier. Right? And so the barrier height, you can see, is of the order, or I'm going to say, according to what we have discussed till now, it is exactly equal to the difference of the work function of the metal minus the electron affinity of the semiconductor. Right? No, is that correct? Yeah, that is correct. I mean, so that minus this, right? So that's the way by here. Now, okay, so that's a simple theory. If your doping in the semiconductor is reasonably, so you can see that it is actually if the doping makes it somewhat n-type when the Fermi level is close to the conduction band, then the electron affinity and the work function of the semiconductor are almost equal, right? If the Fermi level is very close to the conduction band, right? Because the electron affinity is that, Fermi work function is that, and if Fermi level is right next to the conduction band, they're almost equal. Right? So also a good estimate is this barrier height is roughly the difference of the work functions of the two materials. So this is kind of a rough estimate as well, but this is more accurate. Right? Yeah. Yeah, so I said that if your doping in the semiconductor says that the Fermi level is very close to the conduction band, then the electron affinity, Q chi s, and the work function, which is from the Fermi level, are almost equal. Therefore, I can also say that the barrier height is roughly equal to the difference of the work functions of the metal and the semiconductor. Yeah. And again, so if I take as an example silicon, and so this is about 3 point some eV, as we saw. If you choose a work function of a metal of about 4.5 eV, so this will be about this can be half a eV, it can be 1 eV, depends, right? So it depends on the work function of the metal. You can have a barrier height that is very small, or it can be, so you can put your work function of the metal here, or here, or here, depending on the choice of the metal, right? And you can see right away that if you want to make an n-type contact to the conduction band of silicon, your work function of the metal should probably be very close to the electron affinity of this material, right? That's a good, so it's a low work function metal to make an n-type contact to the conduction band. To make a valence band contact or p-type contact, it should be at least an eV more, 1 electron volt more, right? So you choose different metals to connect to different bands of the semiconductor. Does it make sense? So, yeah. Okay, so there are a lot of interface effects that happen. You can have broken bonds and defects and all that. I'm not going to talk about that right now. We're going to talk about MOSFETs after the break, where that's a natural point for introducing those topics. But right now I wanted to just talk a little bit about, so maybe I should also mention that we go into great detail into calculating all these things. What is the depletion depth? How does it depend doping? What are the charges, potentials, and all that? Typically in courses on device physics, that's where we kind of go much deeper into that. And in this course, we are not going to try to get into all the electrostatics and junction capacitance and all that sort of thing. But what I want to look at is how does current flow across the junction. That's something we can actually already answer based on all the quantum mechanical picture we have developed for current flow now. Right? Now this is an interesting case, and I've asked you to do it in detail. Okay, so here, let me just point out how, because this is you're working on it, and I by the way, let me just say that so this is the well-known Schottky diode. This is the Schottky diode, and it is the current across this is heavily rectifying, and the fact that it's rectifying is not very hard to understand. If you look at, so it's essentially the IV will look like a very, very low current in the reverse bias, and then when you turn on, it will increase exponentially, right? And so so I versus V will look something like that, and it is the classic diode rectifier equation I naught e to the power QV over KT minus 1. That's the expression for this sort of diodes. And the expression looks very similar to a PN diode, but it's not a PN diode. This is a metal-semiconductor Schottky diode. There's a big difference. Schottky diodes are way faster. They switch much faster. You can switch at terahertz frequency. If you kind of try to make them go at terahertz, they'll follow. PN diodes cannot go that fast. So there are differences between them. And the major difference between a Schottky diode and a PN diode, which we'll talk about a little later, not now, but here it is a unipolar diode. It has only one type of semiconductor, N. Here it's N, or it can be P. So it's unipolar. PN diode by definition is P and N, is bipolar. It has two kinds of, it accesses two bands, the conduction band and the valence band. Whereas the Schottky diode only accesses one band of the semiconductor. Okay, okay, so just to be clear, so all these states are filled in the metal, all these states are filled in the semiconductor, and these states, conduction band states, there are some. Basically, if I were to sketch the electron density as a function of energy now, energy in the conduction band, how will it look? Right? So how will the conduction band, so if I'm trying to plot what is the N as a function of energy, how will I find that, right? The electron density. So electron density is always the product of two things, right? One is the density of states, and the second is the occupation function, or the Fermi-Dirac function. Let's sketch the Fermi-Dirac function. We know that. If the Fermi level is here, the Fermi-Dirac function is going as 1, 1, 1, and then it reaches 0.5, and then it goes down exponentially, right? That's your Fermi function. It's f of E, right? Does it make sense? So that's very clear. That's obviously at a finite temperature. If you lower the temperature, freeze it down, it will become at 0 Kelvin a unit step function, right? So kind of close to that. If you dope it, it's slightly different, but yeah. And the density of states, how does that look? Conduction band, this is a three-dimensional semiconductor, right? So how does the density of states look?
Square root function.
Yeah, it's increasing, right, from the minimum of the conduction band. So density of states is 0 inside the gap, right? There are no states. And then as you start out from the conduction band edge, which is here, it starts increasing as the square root, right? So square root of E minus EC, and then there's all this bunch of terms in the front, effective mass and all these other things. But it's increasing as square root of energy, right? So increasing DOS and decreasing Fermi-Dirac distribution, the product will have a maxima somewhere, right? And I'm going to just sketch it like this. It's exaggerated, but that's fine. So it's going to kind of look something like that. So that's how the electrons are distributed in the conduction band, right? There's a little maxima somewhere. You can calculate exactly where the maxima is, take a derivative of that product and all that. Total integrated electron density is that. That's the electron density that's integrated. We already did that. This is the number of electrons in that band now. Right? So after you integrate it all out, this is an approximation. Exact value is NC, Fermi-Dirac integral of half order EF minus EC over KT. That being said, you have to find EF by solving with your doping density and all that sort of business. But this is a close enough estimate. So now you see that, so those are the electrons in the semiconductor, right? Far out there, right? Here also there are electrons, but there are much fewer. You see minus EF, your Fermi function is Fermi tail is very, very weak now. It's exponentially lower. So you still have some here, but it's very low. Makes sense? There are very little electrons here. and here even less. These are, I mean, I'm sketching this greatly exaggerated, but you know, these are exponentially decaying, so you shouldn't be able to see it in a linear plot by this time, right? And if I go deeper into the semiconductor, on the other hand, this thing is exactly the same. They all look exactly the same. Right? Carrier density as a function of energy at those points. Now let's turn around and look at what's the business in the metal, right? What's the electron distribution in the metal, right? So in the metal also, you have a band, right? You have a band like this, you have a band like that, and you also have a Fermi function. So exactly the same Fermi function as here. When you are at equilibrium, it's exactly the same. Right? So as a result, you also have a tail, and depends on the density of states of this whole band. Maybe the density of states was, I don't know, it kind of started out like that and it closed like that, and you are here, maybe the density of states going down or something like that. It is behaving in some way, and maybe the carrier density could have a maxima or it may not, but regardless, there is a tail of Fermi-Dirac distribution, right? There's a tail of Fermi-Dirac distribution there too, in the metal. Right? So there are some electrons, and this is very important concept now. There are always, at finite temperature, there are always some electrons for whom there is no barrier, right? So this is a barrier only if the electron energy was lower, right? But at any finite temperature, there are always some electrons that classically are allowed to go from here to there. This is, the barrier is not high enough, right? Does that make sense? So that tail will always have some, there will be always a little bit of carriers that are, you know, here I'm exaggerating, it's vacuum level, it can't be above that, but you know, this is a scale problem at this point. But so there are some carriers that will go over, that in principle can go over, right? And similarly, there are some that can go from here to there. And this traffic, I mean, the difference of the two is the net current across the junction. That's all the Schottky diode current is all about, right? The difference of the two currents due to the tail from the semiconductor minus the tail from the metal is the net current across the junction, right? When you do not apply any external voltage, you can see that the two must be exactly equal, right? Because, well, you can't have current without external voltage. And therefore, that gives you, okay, one condition that, you know, how the two would look like and all that. When I apply an external voltage, all I'm doing really is, so I have a semiconductor, I've formed an ohmic contact on this side. I've connected with my battery to this Fermi level. So what I'm doing really when I apply a voltage is I'm connected to the Fermi level of the metal through my external, you know, wires that I have used. I've used a wire, and then I have an external battery, right? So with this battery, what I'm really doing is I keep, let's say, this Fermi level fixed, but I am moving this Fermi level now, just like we were talking about for that 1D conductor. That's all I'm doing. When I connect it to a battery and I apply a voltage, let's say I apply a negative voltage here, then what I'm going to do, meaning if I apply, okay, let me sketch this slightly. Okay, so when I apply a negative voltage to a terminal, I'm putting more electrons into it. If I apply a positive voltage to a terminal, I'm pulling out electrons from it. Negative means I'm trying to charge it more negative with electrons. So if I apply a negative voltage to the semiconductor, and let's say we can always keep one of them fixed. Let's say this is grounded, it's not changing, and I apply a battery with minus 0.5 volts. What I'll do is I'll lift this thing up, you know, and you can see physically I'm raising the Fermi level. Why? Because I'm pumping in more electrons into that system now, right? And if I apply positive voltage, I'm pulling out electrons, so I'll lower it, right? Right? So negative bands will bend up. I'll pull the bands up. Positive voltage, I'll pull the bands down. This is very important. I mean, the order, just to remember it, you should just think when I'm applying negative voltage, I'm pushing in more electrons into it, and therefore I'll raise the Fermi level. Right? So that's go up in the band diagram picture. And so you can see right away that if I apply, but the diode, as you know, turns on. The way I've sketched it is positive voltage here, right? It's turning on. So the way it's typically thought about is you ground this and you apply the voltage here. It's actually the same deal, right? So it's just turned around a little bit. Anyway, so if I raise this, what happens, and this is the second probably most important part about any heterojunction, this is the metal semiconductor. The barrier height here between the two is not going to respond, is not affected by external voltage. It's locked. Once you determine the two semiconductors, you chose your metal and the semiconductor, you have a difference of this, it's locked. It's not dependent on any external voltage. You can't change it. So that's the thing. So the barrier height remains the same. What does that mean? It means that any electron current that was flowing from the metal into the semiconductor is not going to change because of the external voltage, because those electrons are seeing that barrier still, right? Does that make sense? But look at the barrier for this one, right? So here, let's say I applied 0.5 volts, my bands will now look like that, right? I raise it by 0.5 volts. The Fermi level pulls up, and the conduction band also goes up, right? And therefore now I have lowered the barrier height for electrons, like say this slice of electrons that could go from here. I've lowered it by the amount of voltage I applied, right? So I've lowered the barrier linearly with voltage. Does that make sense? I basically just pull the whole thing up, right? And therefore, if I lower the barrier linearly, these currents depend exponentially on the barrier height. So the current will go exponentially with the voltage. And that's why you get this thing here, right? E to the power QV. So, and as a result, I mean, that's really the key difference. And if you get this concept, I think all rectifiers, transistors, anything where you can get 8, 9 orders, 10 orders change in current is because you are exponentiating a linear function. I mean, so basically it's the voltage that gets tied into the amount of current. Yeah.
So just recap real quick. So positive bias by definition is the terminal in which you lower the barrier height.
Right. So whichever terminal you apply positive voltage on, a positive bias, you're going to lower the Fermi level because you're pulling out electrons. That's how you can charge something positive, right? You pull out electrons. And those electrons, and if you're applying negative voltage, it may be pumping in electrons, so you're going to raise it. Fermi level goes down with positive bias, goes up with negative bias. Now, just to be clear, those electrons that you have, for example, here you apply negative bias, you actually pumped in electrons, but those electrons actually have come from here. It's not like they came out of the battery. The battery is also charge neutral. So the whole system remains charge neutral. So if I applied that, and what happens is the depletion region will kind of shrink a little bit, and as a result, the negative charge in the metal will go down a little bit, and the depletion region will shrink a little bit. So that's something that happened. But now it's a non-equilibrium situation. There's going to be a net current flow. Now let's just look at. Was there a question? No. Let's look at it. So that's to me, it's very important that you get the qualitative conceptual picture first, because after that, the quantum and stuff, those are details. You can handle those, I think. But this is the important part. This is the conceptual part, and you can see where it comes from. So how does it connect to the EK diagram? Basically, difference between two crystals, semiconductor and metal, and then you join them. There's a drive to equilibrate the Fermi levels. As a result, there's depletion and accumulation, depletion on one side, and then some carriers accumulate on the surface of the metal. There's a barrier that's built up. And in a semiconductor metal junction, the barrier height is locked, and it's actually the same if I take, instead of a metal and a semiconductor like what we're doing here, I can take a semiconductor heterojunction. For example, I can take a semiconductor with a band gap like that, and another semiconductor with a band gap like that. That's a heterostructure now, right? I don't have a metal here. And let's say my Fermi level of this, before I join these two semiconductors, my Fermi level is here, and the Fermi level of this is here. I have placed them by doping EFB and EFA. Let's say, right? I put them together. Now, what will happen is this is going to lose electrons, right? Because it has a high Fermi level, it's going to lose electrons, and therefore what's going to happen is I'm going to sketch out the band diagram now. So it's going to, this thing will bend down because it has accepted more electrons. It is more n-type now. It's going to bend down. The conduction band will come closer to the Fermi level. That's a sign that you have more electrons, right? And then the band offset, which is delta EC, is not changed. in that process. The band offset stays the same. Let's say it's kind of like that. And then this side has lost electrons, so it's going to again do that, and you get a band diagram, which looks something like that. And this part is very much like the Schottky barrier that we talked about there. This is what's called a heterojunction Schottky barrier. Instead of a metal, you have a semiconductor here, and that's okay. This is also a heterojunction, right? And this thing is locked. So you can actually form a little 2D electron gas here and all that business, but we don't need to get into those details here. So valence band, conduction band. So let's look at how would one go about calculating the current, and we can kind of end the discussion after that. How would one go about calculating the current across the junction? And it depends very much on the dimensionality of the problem. And let's look at a 3D problem, which you guys are doing in your assignment. So in a 3D problem, what you have is you have your metal. I'm going to draw it upside, vertically instead of laterally. So let's say I have a metal and my semiconductor like that, right? And then it's 3 dimensions. So it's physically a mesa. Those of you who process things in the clean room would, if it's familiar, you can take the metal semiconductor and etch it down, and this semiconductor may be n-type, and you make a contact to the semiconductor, ohmic contact somewhere here, and then you connect these two things to a battery. So that's how you actually measure the IV current versus voltage characteristics of this stuff. Yeah. So physically, what we're going to do is look at this problem so let's look at the electrons in the semiconductor, right? The electrons in the semiconductor are all in the conduction band, right? The electrons in the semiconductor are in the conduction band, and you can choose whichever point you like to calculate the current. Let me just say that there's one point typically when we calculate the current that makes life very easy. Everything else is kind of harder, right? But you can in principle do it anywhere. And here I've suggested you look at the edge of the depletion, where you have electrons that have reached equilibrium, which are like everywhere in the bulk. So at the edge of depletion, this is the energy versus space diagram, your is the energy band diagram. But let's look at the k-space picture of what's going on at this edge of depletion in k-space. In the k-space, physically, what's going on here is it's a 3-dimensional semiconductor, so their electrons can move in kx, ky, kz, right? All 3 directions. And let's label this direction as the z direction, right? Okay. Let's label that as the z direction. And so here you have electrons in 3-dimensional k-space. So let's sketch how. So I'm looking at electrons at the edge of depletion somewhere here. And we're going to look at kx, ky, kz. Now, what is the so the minimum point is so let me write down the energy of an electron as kx, ky, kz. How will I write the energies of the electrons in the conduction band? Right? What's the minimum energy for them? Right? It's the band edge, right? EC. Right? So that's the band edge, EC. That's the minimum energy. And then anything above it is all because of kinetic energy, like h squared k squared by 2 m star. Now that's where all the extra energy comes from, right? So the energy will be EC plus Planck's constant square times twice the effective mass of the conduction band, the curvature, right? Times kx squared plus ky squared plus kz squared, right? The electrons can go all 3 k directions. In other words, I'm going to just sketch something here which, that's only valid actually at 0 Kelvin. But there is one can think there's a little surface, a sphere like that, and you have electrons that are inside that. The sphere is not at room temperature. It's diffuse. It's not very sharp, but at low temperature it will be very sharp surface, But inside it, you have these states that are separated. Maybe you can tell me what is the separation between any 2 k states here. Yeah, it's 2 pi over the macroscopic dimensions, L, X, Ly, Lz, all that. Let's say it's a cube. So that would be 2 pi by L. in that direction, 2 pi by L vertically, 2 pi by L all directions. So there's a grid, right? And those states are what are occupied inside that grid. And if I go in and find, let's look at this state here, K state, right? In that grid, right? So we have an expression now for the current being carried by that state. These are all block states, right? From the band structure, we've solved the whole thing. So the current, electrical charge current that is being carried by that state is Q. You can do all your GS, GV, sum over group velocities, 1 over h bar, gradient in the K space of Ek, right? Times mod psi K squared. I'm just going to pull that down, write it as 1 over L cube. Right. And I'm summing over all Ks. Most important thing I have not written yet is f of K. What's the occupation probability of that state K? Right? So that's your current due to state K. And this is current due to state K. This is the net current, the total current. Right? And how do I evaluate this quantity? That's trivial because I already know what is my E of K, right? I can just do the gradient in K space. It's a function of K, Ky, Kz. I just apply that. And this is a parabolic expression, so it's very easy. It's basically just get h bar kx by m, h bar ky by m, and all that, right? But let's look at this problem, and you can tell me. So if this is my, what we are calling a z-axis and x and y, right? Which k's am I really interested in this problem? It's mostly along one direction, right? Kz. That's really what I'm interested in this problem, right? So all these states have different values of velocity. This state will have a radially outward going velocity, but it will have a y component, x component, and a z component. I'm really interested in this one, right? All the rest will always give a 0, right? They'll you can see now, physically what's going on is, the states in the upper hemisphere here are going upwards in general along z, right? States in the lower hemisphere are going downwards, right? In this picture, this minus kz, this is plus kz. We're interested in plus kz, right? The ones going in that direction. Yeah.
Does this go back to like the last exam with the circle, but in this case we have a sphere that's just
yes,
shifted up?
Pretty much. It's shifted up. Right. So I'm getting there. So it's here. What you're doing is when we come to this f of k, we have to be a little careful with what is f of k, which states can actually make it. So we just, but it's very similar. I mean, most of these are similar. Once you determine your barrier height, that will determine which states can actually make it. So, but here, so if what I'll do is then I have to find out, kz, and you can do it in many ways. One of the things I can suggest is you can transform these coordinates into spherical if you want. Kz would be like k cosine theta, where theta is the angle with the z-axis, right? And you go down here, this would be a phi, and all that. So you can do a spherical coordinate if you want. I mean, there are many ways to do it. You can do it in linear too, but this may be easier. Kx would be like k sine theta and cosine phi, and k sine phi sine theta, something like that. Okay, so these are standard, spherical coordinate transformation. But what I'm trying to say is when you sum it, I'm only interested in kz here, the z component of it, right? You can evaluate all the others; they will all integrate out to 0 at some point. But this is what I'm interested in, and I do this L cubed, and I integrate over 3-dimensional K space now, right? 3D K space. 3D K space is d cube k, but I'm going to write down the spherical notation k squared sine theta dk d theta d phi. So I'm going to write it like that. That's the spherical one, right? Divided by 2 pi over L whole cube. Right? That's the volume of each grid point, and so the L cube as usual should go away, and then I have a group velocity. But I know the group velocity is going to be h bar times kz over m star c. That's all going to survive. Everything else, y and x and y components are going to integrate to 0 on both sides. And the f of k is the tricky one now, right? So f of k is where you have to think a little bit that maybe you can help me. Which states can actually make it to from here to there. Right. So yeah. So let's look at it from 0 to infinity, but the 0 is where, right? So see, we are saying that there's a barrier, right? And the states that can make it are the ones that have energies larger than the barrier, right? And obviously, I'm controlling the number of those states with external voltage, right? By kind of with a plunger sort of thing, so kind of pushing it up or down, right? So what I'm trying to get to is let me ask you a few questions. What about this state? Can it make it to the top in the lower hemisphere? It can't, right? It can't make it to the top. What about the state at the gamma point at 0? Right, it can't. Very interesting question now. What about the state very close to this? Can it make it or can't it make it? And you'll realize that actually that can't. It cannot make it. Why? Because its energy is somewhere here, or it's still here. It's not, doesn't have enough energy to go over that barrier, right? So if you look at this carefully, you write the total energy of this, right? The total energy must be larger than the net barrier height, right? And that restricts the amount of k states that can provide a current. So it must have a kinetic energy of this much, right? It must have a kinetic energy of this much. All the states above that line are going to go, right? So there's a natural demarcation now in the k space, and that barrier height determines what part of this k states will actually make it. And let me just say that you probably can think a little bit, but you will get a very interesting picture like that. So there'll be only states something like that will make it, right? Will make it. And what you'll see is there are some states that are kind of most of their energy is because they're going in the z direction, right? Here's a state. All its energy is because it's in the z direction. Here's a state out here where it's going in the z direction, but a lot of its energy is in the xy direction, right? Classically, that electron is kind of going, like that, right? But it has a slight z component. It will actually make it. It will keep going, and then finally plop over to this side, right? So that's kind of, so you have to sum over a restricted set in k space, and that's what this integral and the function f of k here that you have to use. It restricts the k space into this, sort of a shell, you might, right? So and that shell depends on the voltage. When your voltage is 0, the shell volume is 0. There's nothing going. There's essentially they'll equilibrate. But when you increase the voltage, you increase the size of that shell. You can shrink and then more and more possible carriers. Yeah.
That shell, that's the entire top hemisphere that's pointing in z positive direction.
Yes. That's right. It's in the positive part. There's also a shell bottom, but that's not going from the semiconductor to the metal, right? And so when you integrate this, you may evaluate. So kz will be k cosine theta, and depending upon the geometry of this k space, you must fix your theta and phis and all that. Phi will go 0 to 2 pi. You just rotate it all around, right? But theta, you have to be a little careful. It can only go from 0 to pi by 2, right? Not the other half and all that. Yeah.
Can you explain again what you meant by just the positive part of the sphere? Or are you just talking about one octave of the sphere?
Oh no. So yeah. What I'm trying to calculate the net current of electrons going from the semiconductor into the metal in that direction, right? So that means the kz must be greater than 0 because that's the positive kz. Yeah, just the upper hemisphere. But then even within the hemisphere, because of this energy barrier, you have a restricted shell that's actually allowed. So yeah. And there's a question. Yeah.
So the lower limit of the shell of the sphere is EC, right?
So so this is interesting. So you're saying what's the lower limit? So this is an integral in k,
Yeah.
right? So and depending upon what you get as your, there'll be basically a minimum k, which will be determined by the barrier height. Yeah. So you have to kind of get that, and then once you do that, let me just say this is a little harder way of doing it. In traditional books, you will see a more diffusion sort of classical picture, which will get you here. But since we have developed all this stuff with quantum, we should think of it that way. This is actually physically what's going on in the quantum mechanical picture. There are electrons in the conduction band that are going, in all three. Basically they have a spherical distribution of velocities. These are group velocities, and the ones, basically the ones that have enough kinetic energy to surmount the barrier, will make it. That's the way to look at it, right? So, and then you will get this whole expression from this sort of analysis. And right, so this is the Schottky contact. A lot of the early work was done by Hans Bethe of this current. Is thermionic emission current. It's similar, and we will get a Richardson coefficient in the front, which is related to all the band parameters, effective mass, and all that sort of thing. So you can use this to measure effective mass of a semiconductor, and then so on. Right? And the same theory pretty much carries over to semiconductor heterostructures or other heterostructures too. But I think this is I want you to kind of spend some time thinking about it and solving it, because if you can solve this, pictorially looking at it and geometrically looking at it, this is covers a very wide range of quantum transport problems. I mean, transistor, heterojunctions, all that stuff kind of follows from something similar. Okay, good. So we can stop here, and you're solving it. So I'm also available on and off tomorrow. If you want to come by, discuss something, just drop me an email. We'll find a time to discuss a few more things, and okay, and we'll meet after the break then.